Moving on, we encounter a special case where the work non-conservative equals 0. For example, when one neglects friction in a problem. We see here that work non-conservative equals delta KE plus delta PE. Don't forget that you're accounting for potential energy spring plus potential energy gravitational if both are in the problem. Then we see that work non-conservative equals 0. Therefore, 0 equals delta KE plus delta PE. Next, we expand our delta KE and delta PE into 0 equals kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. If we simplify this, we can see that kinetic energy final equals potential energy final. When we simplify the problem, we see that kinetic energy final plus potential energy final equals kinetic energy initial plus potential energy initial. Therefore, total energy final equals total energy initial, and energy is conserved when work non-conservative equals 0. When trying to account for what types of energy are in a problem, there are 3 basic questions you can ask yourself. Is it moving? If so, then you must account for kinetic energy. Is gravity involved? For example, is the object on a cliff or on a shelf? If so, then potential energy gravitational must be involved. Finally, is there a spring? If there is, don't forget to account for potential energy spring. To further understand the potential energy function, we can look at the derivative of the function. As we already know, work conservative net forces equals the negative change in potential energy, or negative delta U. We know that the work done by conservative forces equals the conservative force dot dx, the integral from xi to xf, equals the negative change in potential energy. We then see that this equals the negative u of x final minus u of x initial. Therefore, the integral from xi to xf of f dot dx equals negative u of x. We can take the derivative of this again and see that the integral and the derivative on the force side cancel, leaving us with f dot dx equals negative du of x over dx. Finally, we can see that f of x equals negative du of dx. Therefore, force equals the negative derivative of potential energy. When solving for potential energy, we must remember that we're only concerned with the change in potential energy. If we don't know what potential energy is relative to, it is useless. For example, a ball sitting on top of a cliff. We don't know how high the ball up is. For example, a ball on a cliff. If we don't know how high up the ball is, we can't know the y or the h in the formula mgh, and therefore the potential energy has no use to us. Now let's try and visualize potential energy, particularly for a spring. In the first example, we see the spring is fully stretched, and therefore the potential energy is at its max. As we know, when the potential energy is at its maximum, the kinetic energy must be at its minimum of 0%. Now looking at the second box, we see that the box is completely moving, but is not stretched or compressed. Therefore, we see that the kinetic energy is 100% and the potential energy is 0%. When the kinetic energy is at its maximum, the potential energy is at its minimum. Next, moving on, we see that the box is completely retracted. We see that the potential energy is 100% because of the compression, and the kinetic energy is 0% because the box is not moving. Once again, we move down to the fourth box and see that the box is moving at 100% kinetic energy, and therefore potential energy is at its minimum of 0%. Finally, the string is completely stretched out once more, and the potential energy is 100% as the spring is not moving and the kinetic energy is 0%. Somewhere in between these values, when the spring is neither completely stretched nor moving only on its own, we know that the kinetic energy equals 50% and the potential energy equals 50%. Therefore, when we add up the two percentages, it equals 100%, and that's always our goal when we're conserving energy. The potential energy well is another way of looking at this same point. As the potential energy at the origin is its minimum of 0, the maximum kinetic energy is achieved. The inverse is true, as when the potential energy is at its max, the kinetic energy is 0. Looking at this as yet another example, we know that the potential energy is the integral of the force conservative or the work conservative forces. We see here, once again, that when the force or kinetic energy is at its minimum, the potential energy is at its maximum value. While it may be harder to see in this example, we know that when you add up the values of both the energy, the potential energy, and the force of X, that the two together will equal the maximum energy in the system, and the energy will be conserved. Things to remember from Chapter 8, Conservation of Energy. Conservative forces are path independent. Some examples of conservative forces are the force of gravity and the spring force. Non-conservative forces are path dependent, and they take energy out of the system without replacing it. For example, friction and air resistance are non-conservative forces. We know that the work non-conservative plus work conservative equals delta KE, or work net. We also found out in this chapter that work non-conservative equals delta KE plus delta PE. Potential energy, or PE, is energy that can be transferred into kinetic energy. It has the potential to be transferred into kinetic energy. Moving down, we see that potential energy is represented by delta U and equals the negative work done by conservative forces. Potential energy, the derivative of potential energy, also equals F of X. When you're trying to determine what sort of energy is in the system, there are three questions to ask yourself. Is it moving? If so, kinetic energy is involved. Is gravity involved? If so, potential energy gravitational is involved. Is there a spring? If so, potential energy spring is involved. Finally, when we're looking at a graph, when the kinetic energy is at its maximum, the potential energy is at its minimum. And then when the kinetic energy is at its minimum, the potential energy is at its maximum. When you add the two together, you should get 100%, or 0 when energy is conserved.